So first of all, this course arose about nearly 3 years ago now in the context of the great powers competition. The Navy has been getting extremely concerned about this. A lot of the competitor countries have been speaking about using AI to gain a competitive advantage, and our Navy doesn't want that to happen. And our Navy feels like others are catching up, and we're trying to stay ahead and want to get extremely smart in this field. So that was the context here, and the purpose of this course was to give those who've heard a lot about AI the opportunity to come and learn something new, get a sense of the field, and then if you want to dig deeper, you know where to dig. So this is an old field, and some of you probably already know that it's been plagued by a lot of hype. People exaggerated claims about what could be accomplished with artificial intelligence, and it's just been a problem. So what we want to do is help you see where the hype is so you can avoid it and not get sucked into it. And we secondly want to give you enough language and vocabulary that you can talk intelligently about AI with other people. And we also want to give you a sense of the overall framework of the AI field so you know what the field looks like. So I'm a computer scientist. I'm a professor in the computer science department. I've been here at NPS for 20 years now. I've been teaching computer science, believe it or not, for 55 years. So I've seen a lot of computer science come and go, and I've seen the AI field grow up and mature into what we have today. For a long time it was kind of an obscure field, but in the last 10, 15 years it's become a very important field. My first experience with AI was not a great one. It happened in 1968. I was interviewing at Stanford for a faculty position, doing the interview rounds at that time, and they said they wanted to show me their AI lab. So they took me over to their AI lab, and they were very proud of a demonstration they had with a robot arm that stacked blocks. So the idea was there was a little table, a black tablecloth, and 3 white cubes, and they said I could place the cubes anywhere I wanted on the table, and then they pushed the button, the robot arm would come and look at this arrangement with a TV camera and then pick up the cubes and stack them into a stack. And so I was, completely amazed by this. That's pretty amazing. Tell me more. How does this thing work? And so the curious guy, they open up and they said, oh, here's how it works. And well, it turns out that the TV camera is taking advantage of certain properties of geometry, where if you have 3 cubes in a picture and all you can see is the outline of the 3 cubes, there's enough information there to tell exactly where the 3 cubes are. So there's some bit of geometry involved with that. So the TV camera would trace out the outline of the cubes, figure out where the cubes are, and then it could position the arm to pick them up and stack them. This geometric theorem didn't work for 2 cubes or 1 cube or 4 cubes or 5 cubes. It only worked for exactly 3 cubes. So this whole thing, they had no idea how to generalize it. So they couldn't put more cubes or fewer cubes. They couldn't put different size cubes. They couldn't put different objects there. It was just this particular arrangement, and that was it. So I said, this whole thing is kind of almost like a fraud is the way I reacted to it. Like it could only do that one thing, and it wasn't anywhere near like any kind of general AI. So I got turned off. I said I don't want anything to do with AI, and spent most of my career with operating systems and networks, which were very productive. But in the last few years, as this has grown up and AI has become very important, I've come around and I'm now very interested in AI and the kinds of things we can do with it and helping people understand what it does. So that's what we're here about today. So what I want to do today is give you an introduction to the big picture of what we're going to talk about in this course. And the main thing we want to focus on today is that the machines that they're called AI machines, have various learning abilities, and we can put them into a learning hierarchy, with machines higher up being more powerful in what they can learn than machines farther down. So that's what we're going to look at today, and then this is going to be developed by the speakers in the course. They're going to look in more detail at each of these kinds of machines, what they can do, and then look at cross-cutting issues like ethical issues and automation issues. Our reason for being interested in a hierarchy of machines is actually inspired by old computer science. When I was a graduate student in computer science, I learned that computing machines could be arranged in a hierarchy of machines, with some machines being more powerful than other ones. And they had 3 different kinds of machines that we learned about. One was called a finite state machine, which is a simple machine with a finite number of internal states. It's like a controller, simple controller, a thermostat for your house or something like that. Is a finite state machine. And so we learned about those, but those are the least capable. Then there was another kind of machine that was called a push-down automata. The word push-down means that as you put input into the machine, it gets pushed onto a stack, and then you pop stuff off the stack. Some calculators work like this. So this type of machine turned out to be very useful for building compilers. So with this type of machine, we were able to develop a very powerful compiler technology so that you can compile programs into machine code and get them to work properly. And the third kind of machine in this hierarchy was called the Turing machine, named after Alan Turing, the guy who was a famous cryptographer and computer pioneer in the 1930s. And he invented a mathematical machine which got to be called the Turing machine that mimicked what people thought computers could do. And it was such a simple machine, but could do anything any computer could do, and it became famous, and it's called the Turing machine. So in the artificial intelligence field, most of the machines that we'll be looking at are powerful enough to do almost any computation, so they are potentially Turing machines. And what we're going to be doing is not looking at computational power, but looking at learning power. So if one machine can learn stuff that another machine can't, we'll say that this machine is higher up in the learning hierarchy than the other machine. So that's basically the idea, is this hierarchy of possible machine types motivated by our experience in computer science with a hierarchy of computer types, and looking at how able these different machines are to learn new things. So we're calling this course Harnessing AI. The purpose in the course is to explore the questions, what is artificial intelligence, what is AI? And there's an associated term with artificial intelligence called machine learning. You've probably seen this before. Frequently, when people write down the acronyms, they write AI/ML. And AI means artificial intelligence, ML means machine learning, and most of us don't know what these terms actually mean, so that's part of what we're going to talk about today. The third question is, what are the benefits and risks of artificial intelligence and machine learning, and what is their military significance? In the process of doing this, we want to establish a common language for talking about AI and precise definitions for these terms that we hear: artificial intelligence, machine learning. We also, in the process of doing this, want to cut through the hype. And the little motto down at the bottom is, don't mistake utility and speed for intelligence. So just keep that in the back of your mind as we go along. Don't mistake utility and speed for intelligence. Here's something interesting about the AI field. The AI field was founded in 1956 to study the possibility of building computing machines that might be intelligent, that could perform intelligent functions. And this field has been buoyed by enthusiasm, lots of enthusiasts. It's also been plagued by hype and overpromising. This diagram here shows evolution of the field over time. So the horizontal axis is years starting in 1956 going up to the present time, and the vertical axis is the amount of interest in the field. You can see there was interest growing up through approximately, 1974. A lot of initial good developments in artificial intelligence during that time is called the golden years. And then something happened and a lot of people lost confidence in the field. And all of a sudden the interest dropped off, the research funding dropped off, and everybody was very unhappy, and they gave it the name AI Winter. And then they recovered from that and started doing new things with AI, building up again to another crescendo, and then something went wrong and a second winter set in. And then finally, that was, we started to emerge from that around early 90s, and we've been growing ever since, and we're now reaching a even higher interest at the far end. And I have to tell you that not everybody is sanguine about this. There's been a recent article, for example, in the War on the Rocks, where somebody said that in the Defense Department, there's still a lot of hype and overclaiming going on, and that's setting us up for a possible third AI winter. And we don't want that to happen, obviously, because if you're in the middle of a great power competition, you can't have a collapse of support for studying an AI. So this field is kind of funny in that regard about the way it's had these boom and bust periods. The rest of computer science hasn't had this problem. This is a slide you could look at in the handouts, but in the fine print underneath each of the 3 growth periods, there's a list of technologies that were produced during that period and which showed the power of the AI technologies. So some of the early things are like speech recognition and board games. And then in the middle, you see more advanced things like expert systems and statistical inference. And then in the last column over there, you see a lot of stuff that you hear about today, like data analytics, image recognition, swarms, somebody was just mentioning swarms, and cyber defense and offense being colored by what AI can do. So when you look at this in the handout, you can see there's been quite a few technologies created during these different periods of boom, and they're significant and important technologies. But that doesn't answer the question of what is AI. So these pictures here give some popular impressions of what AI might be. So the upper left picture is a picture of the Korean Go expert, Lee Sodol, who a couple of years ago was beaten by a machine called AlphaZero. And Go has previously been thought of as a game that's so hard that no computer could do it. And all of a sudden somebody comes up with a machine that could play Go as well as a grandmaster. So you see him sitting in the background trying to figure out what his next move is going to be, and the machine beat him. And down the lower left in the picture is one of the Alexa tools, one of those boxes you could talk to and it does things for you. So that's another impression of AI is little boxes that you can talk to and they do things for you. Then the middle bottom there is a more sinister view of AI that comes out of Hollywood. This one appears to be from Terminator movies. So a kind of black idea about what can happen with these machines. And then over on the right is a more serene picture of a bunch of birds flying around in a swarm, and what kind of intelligence do birds have that allow them to form a swarm and follow each other around in the sky like they do. And this, of course, idea is becoming very interesting for swarms of drones these days, about being both offensive and defensive swarms of drones. So, we still haven't answered the question. We just said there's four different impressions of what AI is. They're not all compatible. So what is AI? Well, the hang-up is not on the word artificial, because artificial is pretty obvious. It means we get a machine to do it. But intelligence is where we get hung up. So what is intelligence? And can we produce it artificially? And first problem we run in is intelligence is not well defined. When you get people to say, what is intelligence? You get into these long conversations that never quite lead to a precise definition. Among the kinds of things that we talk about are different kinds of intelligence. Some of them aren't even human, like ant intelligence or bee intelligence, or dogs and cats are said to be intelligent in their own way. And chimpanzees and others are all these kinds of animals are intelligent in their own way, but not the human way. So, what is intelligence? What's the human way that distinguishes us from chimpanzees? Nobody has any clear idea. To make it even more fun, there's a problem I call the elusive goalpost problem, is that you pick something, people say, if a machine could do this, it would have to be intelligent. And then a few years later, somebody actually gets a machine to do that, and then you look at it and you say, that can't be intelligent, a machine did it. So, what do you do with this? If a machine could do it, it's intelligent. Machine just did it. It can't be intelligent because the machine did it. So what is intelligence? So you'll not find a clear answer to that question. It intrigues many people. A couple things we do know about it. First of all, intelligence is not speed. So we know how to build computers that are really fast. A human being can do about one arithmetic calculation a second. We have computers that do 1 billion and 1 trillion per second. So that means machines can do calculations that humans can't possibly do. And your laptop, or my laptop, your laptop, and your nearest computer, supercomputer, are fast, but they're not intelligent. So please don't confuse speed of the machine with intelligence. Some of you may remember a famous statement from the science fiction writer Arthur Clarke, who said, any sufficiently advanced technology looks like magic. We have that problem here. So if it goes fast enough, it looks like magic, but it's still a machine. It's just a very fast machine. And if the machine is simulating an intelligent function, when you start out by saying, if a machine could do that in function, it must be intelligent, so we find a machine that's fast enough to do it, and then we say, it's just a fast machine, it's not intelligent. So please don't confuse speed with intelligence. Is there a scientific definition of intelligence? If we had one, we could use it to see if we could build a machine that was intelligent. Well, there is no scientific definition of intelligence. In fact, many other fields have a similar problem in their fields. One of the examples I like is biology, which is a field that says we study life. When is an organism alive and when is it not alive? And there's no scientific definition of life. What the best the biologists can do with that is they have criteria, like there's 7 criteria listed out here: nutrition, respiration, movement, excretion, growth, reproduction, and sensitivity. And biologists can say, here's a new organism, and have a little checklist and see how many of these different features of that organism are present. And if enough of them are present, you'll get biologists saying that's a live organism. If too few of them are present, the biologists will say it's not alive. Neuroscientists who study brains have similar problem in neuroscience, the consciousness problem. This is something hospitals and doctors wish they had a precise answer to. When is somebody who is comatose, are they still conscious? How could you tell if they were still conscious? Well, nobody really knows how to do that. So it's always a ethical problem, is how do you tell if somebody's conscious or not? And certain things like eye movement and brainwave measures are not considered to be definitive in that regard. They don't definitively say whether somebody's conscious. So this idea that we're in a field where we want to see what is intelligence, could we automate intelligence, is similar to biologists trying to figure out what's life and neuroscientists trying to figure out what's consciousness. Nobody has answers to those things. Well, let's go back to the words that we're using and see if we interpret them literally, what do they mean? So the two words we're using here are artificial intelligence and machine learning. So when we say artificial intelligence, what are people trying to say? Well, very high level, we're trying to say they're trying to develop intelligent machines. And this means they could do all sorts of things that human beings could do. They could think, they could have intuition, they could make conjectures, they have imaginations, they have intentions, they make and keep commitments, they're conscious, they're cognitive, and they're self-aware. And there are probably some other things you could think about human beings that might be on that list. So when you take this literally, you say you want artificial intelligence, the question is, could you build a machine that does all these things that we normally associate with human beings? There's some people who say, well, we'll call it artificial intelligence if it could even do one of these things. We'll start small and then we can get bigger after that, but that's still another literal interpretation. What do we mean when we say artificial intelligence? When we say machine learning, what we're talking about at a very high level is designing machines that learn new functions. And places where this has happened is speech recognition, image recognition, games, planning, deep learning, more deep learning, conversations, driverless vehicles, automatic fire control, swarms, and other things of this kind, where the machine starts out as kind of a blank slate and you show it how to do the task, and it gets better and better at it, and finally achieves the ability to do that function. So if we can do that with a machine, we call that machine learning. So the question is, what's the relationship between artificial intelligence and machine learning? Because it looks like from the bottom of this here, what the machines can do is a lot different from what's on that list for intelligent. So with these interpretations, the artificial intelligence taken literally would mean that we're going to build machines that look like human intelligence, and this has never been accomplished. Nobody's even come close to this. It's like an aspiration of artificial intelligence to maybe be able to do that someday. Machine learning, on the other hand, is what we've been doing all along. We've been building machines that learn new functions, and we're getting pretty good at it. And so this is where all the action is taking place, really, is machines that are learning, and where all the military applications are is in machine learning. How can we adapt that to military use? There is a famous test some of you have heard about. Have you heard about the Turing Test? It was invented in 1950 by Alan Turing, who said, hey guys, we don't know what intelligence is, so we can't use that to define what we mean by an intelligent machine. But we can define an imitation game. So if I have a machine that I can have a conversation with, and I can't distinguish that machine from a real human being, I'm going to wind up saying that machine is intelligent. So he said, let's use this as the basis for understanding whether we can build a machine that's intelligent. So can a conversation machine fool a human interrogator is the question. So here you can imagine a human and a computer, and we're going to try and distinguish between the two of them, and all we get is there's an interrogator who can ask questions of either one, and an interface hides the identity of both of these, so you just see two entities having a conversation, and the interrogator asks them questions and evaluates their answers and finally can say, this one is the machine, this one is the human being. So one of the questions that Turing brought up was, how long does it take the interrogator to distinguish the computer from the human? Is it 5 seconds, a minute, An hour? How long is it before the interrogator can tell the difference? And even if the interrogator could tell the difference, would you then conclude that the computer was intelligent, or would you just say it's another machine having a conversation that simulates intelligence? So nobody has an answer to that question. What the Turing test did was it changed the subjective idea of intelligence to an objective idea of a machine output, which would make it more possible to implement something and test it. It turns out this didn't help. People have been trying to build intelligent conversation machines ever since Turing brought this up, which is what, 70 years ago now? And we haven't gotten close to anything that looks like that kind of conversational machine. This is a lot harder than a lot of people thought it was. So, now we're left, so we kind of agree that we're not going to agree on intelligence, but we could agree on what machines could do and watch what machines can do. And so now we need to be a little more precise about what's a machine. Because there are people out there saying human body is a machine. And there's other people, biologists may say, well, in some respects it's like a machine, but in other respects it's different from a machine. So we need to, if we're going to build intelligent machines or machine learning, we need to have some idea of what we mean by machine. So a machine in standard usage is an apparatus of components that automate a process that we humans want done. The machine grants us an advantage, such as amplified force or speed that humans do not naturally have. And the human is either fully or partially out of the loop. The machine can do the job with minimal amount of human help and intervention. And this general idea of a machine automation, a computer is a machine that has hardware and software components. The machine is controlled by software, and the input-output functions of the machine are determined by algorithms. So a computer is a form of machine of the more general type shown in the ideas above. So it's a machine that automates processes people want done, but does it better than people can do it by themselves. So this leads us to the idea of a hierarchy of machines. So we could take the existing machines that we can see in AI and arrange them into a hierarchy by their learning power. So we need to say, what do we mean by learning power? Here it is in blue. Machine, let's call it machine A, is more powerful than machine B if A can learn something that B can't. And this turns out to be pretty easy to find examples of this. So this allows us to compare machines in terms of their abilities and limitations and see which ones are more powerful and make good selections for what kind of machine we need for a particular application. It also gives us a language for evaluating learning machines. This diagram is simply a pictorial view of what I just said. Machine A is somehow bigger and more powerful than B, meaning A can learn stuff B can't. So this is what we mean by the hierarchy. Here is a list of the types of machines in the hierarchy that's commonly used in AI. So this one has 5 levels to it. Starts with basic automation, which automation is an old term that preceded the AI field, and so we want to start from there. This is classical automation, and then we're going to start adding stuff on it that gets automation of intelligent functions. So level 1, which is just above automation, basic automation, is rule-based systems, which are basically standard programming systems. We write programs and the machine does things for us. Next one up, level 2, is supervised learning, which means we're going to show the machine what we want its output to be with lots of examples, and the machine will learn how to do that. Unsupervised learning means we'll let the machine, we don't tell the machine what's the right output. We say, here's the data, you tell us what's the right output. And the machine looks through the data and comes up with outputs. Level 4 is human-machine teaming. We see a lot of this in discussions where we talk about the human and the machine working together, and being able to accomplish things that neither one could do by themselves. The highest level there is aspirational AI. This is all the things that we wish we could figure out how to do, but we still don't know how to do. Okay? It's possible to look at the first part of this as more and more automation. As we learn how to automate more advanced things, we get higher and higher levels. So level 0, 1, 2, 3, and 4 are degrees of automation. And level 5 is above what we know how to do right now. It's our dreams. Yes, sir?
So you'd only call step 5 actual AI. Everything else is just automation and
Well,
very good algorithms?
If you take the words literally, yes. Okay, so if you say artificial intelligence means intelligence has been automated, we don't know how to do that. Okay, we do know how to learn things, but you know, here you get into issues like some of the dreams that people have had about AI have motivated researchers and developers to create these learning machines. So if they didn't have the dream, they wouldn't have the machine. So AI, the dream was influential in that sense. Okay, so I don't want to get hung up on this, because the real issue here is what can we do with the actual machines that we have. Okay, and we have lots of dreams about things we want machines to do in the future, and we're not there yet. So that's the best way to look at this. Okay. Let's talk briefly about the beginning of this level 0, the basic automation, which simply means classical automation of unintelligent tasks. So we get a machine to perform a process. The human is mostly out of the loop. These machines might have internal feedback mechanisms to help stabilize their operation. So for example, autopilot the older autopilots have gyroscopes in them to help them stabilize their operation, but they don't learn anything new. The feedback is used to stabilize. Machine learning can be used in some components of basic automation to help do things. Examples that we put in this category are autopilots, container shipping, robotic warehouses like Amazon's warehouses, and voice response robots. So these are all examples of basic automation. They're not doing intelligent things really, and but they're doing useful things. Next level up is the rule-based systems. So these are program systems that make logical deductions from an input, and they have a database of facts and rules, and they use this database to draw conclusions about the inputs. Early examples of this are chess and checkers. So in the 1950s, some people actually built chess and checker playing machines based on the idea that we'll write down all the rules of chess or checker and have a database full of examples of chess games or checker games to help guide what decisions the machine makes as it plays against a human being. This idea in the 1980s got expanded to include something called expert systems, which are software systems that are supposed to perform the same kind of tasks that a human expert can perform. Examples of systems in this category are medical diagnosis systems, image interpretation, equipment repair, and logistics. Next level up is the supervised learning level. So this means we have machines that we show them what we want them to do, and then they remember that and acquire the function. So the most common instance of this in today's technology is called the neural network. This will be explained to you in future lectures in great detail, so you'll see how they work. But the neural networks are electronic circuits that mimic the structure of the brain by simulating neurons of the brain. And so what we do is we have a neural network, we show it, here's an input, here's the desired output, and we show it example after example after example, and the neural network remembers all this stuff and eventually gets to the point where you're showing an example and it gives you the correct output. So that's called a trained network, when we showed it all the examples, and we now believe that it's learned the function. And now this has brought up all sorts of questions like, what happens when the network is shown a new input that it wasn't trained on? So let's say we have a network of faces, and we've shown lots of examples of faces and the names of the people, and now we showed a new face that it wasn't trained on. What's it going to do? Is it going to give somebody's name that's already there, or is it going to say, we don't know this person? And this, since nobody has, it turns out a lot of these things, we don't have good confidence in what the machine will do with on the untrained data. So this is a research problem that people are looking into, is how to get to the point where we trust the machine to give us a good answer when we show it data that wasn't part of the training set. So examples here are success examples, image recognition, but at the same time, there's weird ways the network can go wrong. One of the speakers will talk to you about neural network in a driverless car that mistakes stop signs for speed limit signs, or actually thinks a stop sign is a speed limit sign because there's a few bird droppings on the sign. A human being wouldn't say that's a speed limit sign. Human saying that would say that's a stop sign with bird droppings, but the machine says it's a speed limit sign. And if you have that machine controlling the accelerator of your car, you're going to have an accident. Unsupervised learning is level 3. One of the problems with supervised learning is you tend to need huge amounts of data, and it's very expensive to train a network. There's been a recent case where one of Google's companies has a network that can simulate some conversations with people, but it cost them $10 million of electricity to run the supercomputer to train look at all the texts, books, papers, etc., articles that it needed to find out how people respond in conversations. So this is a big limitation of supervised learning. So people have asked the question, is it possible to show the machine the data, give it a few base rules, and let the machine do all the work? And there are some applications where this does work. For example, we have lots of data, and we want to group the data into equivalence classes. So these pieces of data are basically all the same. These are the same, these are the same, and so on. And we have machines that'll do that very well. We still need, when we get done, the machine will just say there's cluster number 1, cluster number 2, cluster number 3, and then it leaves it to us human beings to give them more meaningful names. An example of this, early example that I saw was in NASA. Astronomers worked with some AI people and developed a system called AutoClass for automatic classification that would take data from star surveys and group them into equivalence classes. These stars are all similar to each other. And the machine reproduced all the classes known to astronomers, and they said, this has got to be a pretty smart machine to do that. And the machine even discovered a new class that the astronomers hadn't seen before, and then they said, oh, this is a new class of stars we hadn't seen before. So this is very useful, this kind of machine. It doesn't require supervision. Other places where this has been used is the examples recently of chess and Go. They use something called reinforcement learning, which is they're going to watch what the machine has come up with so far, and then if it's a good move, they'll reinforce it so that future decisions of the machine will favor that kind of move. If it's a bad move, they'll negatively reinforce it so in future the machine will not do that again. And they use this type of reinforcement to do the machines that do Go and chess. So with this, once they got it perfected, the machine called AlphaZero was able to learn Grandmaster chess in 4 hours. And it was able to learn Grandmaster Go in 13 days. So there's a pretty significant difference of time there to learn the game. But on the other hand, nobody had been able to get a machine of any sort to do anything useful with Go until this machine. And in chess, the machines that would play Grandmaster chess exist, but they took 30 years to develop those machines. This system figured out how to play Grandmaster chess in 4 hours. So this is a significant breakthrough here, the ability to learn some complex thing in such a short period of time. Level 4 is human-machine teaming. So these are machines that work together with humans. So the human provides the stuff the human is good at, the machine does the calculations fast, and together they get a lot of stuff done. An example of this is what's called freestyle chess, where humans come accompanied with a laptop that plays supercomputer, gives them advice on chess moves, and the team can then beat the supercomputer. Finally, we have level 5, which is the level that does all the aspirational stuff. So I'm going to stop here. There's a couple more slides which will be available to you in the handouts, which just amplify a little bit on this, and tell you to be cautious about things like the hype. That people will make promises about what the machines can do that are actually beyond their power. And we want you to learn how to be smart and say that can't be done by a neural network, or that can't be done by a reinforcement learning system. So there's a few more slides to be available in the handout to help you with those things. So that's it for today. I wanted you to see this idea that we don't have precise language for talking about intelligence. We do have more precise language for talking about machines, and we've built hierarchies of machines that do very important functions and do them well. And sometimes we call those intelligent functions, and sometimes we don't. So I'm going to stop here, and so we're done for the day, and we're going to see you next week.